Okay. So I'm going to take a minute to go over module 14 with you guys. I'm going to share my screen. So here we are in period 5. Going to go to our volcano right here. We're going to go into the modules. So I'd like everybody to do me a favor, go into your science tile, and please make sure that module 14 is available to you in your science tile. If it is not there, please let me know. Aiden's giving me a thumbs up that it is there. Anybody else? Beulah, anyone? Okay, Lynn has it. Thank you, Lynn. Travis has it. Awesome. Thanks, guys. Okay, so because multiple people have said that they have it, it's there for everyone. So we're going to go through it really quick and look at due dates for you guys. So this one here, I only have period 1 through 5 once this week today. So I changed some due dates around. We're going to go through the slideshow today. You all have access to it. Then you guys are going to watch a Bill Nye, and you may have done it already, you may not, but let's just review on how to, 3 people submitted it. Let's just review on how to make a copy of it. When you go into the assignment here, Bill Nye, you're going to go into file, whoops, you're going to make a copy. When you make a copy, you will be able to write on it. Once you write on it, answer the 15 questions, you can hand it in for credit. Thank you for responding. It is worth 20 points, 20. 1 point for each question, and then 5 points for handing it in. You're welcome. It is due, this is the only assignment that's due tomorrow at 11:59 p.m. So we have that one. Then after we do that, or after you guys do that, you will then watch or watch and read and watch about earthquakes. So it talks about the different types of earthquakes. It talks about plate tectonics, which we've already spoken about with Alfred Wegener, right? And we'll talk about that more a little bit in the slideshow. The different types of earthquakes and a little video that goes with it. After that, there's another article on here that has to do with the different types of waves that are found or that are recorded on a seismograph, when an earthquake takes place. So it talks about S waves, P waves, and surface waves. You can read that little bit there. And then you're going to have to fill in what's called a Venn diagram. So here's the Venn diagram, and it says research and list 10 facts to add to the Venn diagram. 10 facts all together, not 10 facts each, 10 facts all together about P waves, S waves, or both of them, okay? These are the things that they have in common. This is only S wave attributes, this is P wave attributes, and this is what they both have in common. You cannot write on this diagram here, but if you click where it says click here, you will get your own copy of the Venn diagram. Then what you're going to do is you're going to embed the image in the discussion post. So you're going to be creating another discussion. Once you put your Venn diagram into the discussion section, you will then comment on either the post above you or below you about any of the facts or if they're missing any facts, right? So we've had Cyan do this already. Good job, Cyan. And then lastly, you have a test to take. Now it's worth 57 points. 57 points is 3 points for each question. There are 19 questions. I'm going to give you a bunch of notes today that are going to help you with this test and with the Venn diagram. My suggestion is that you take your time taking the test. Do not take it in 8 minutes. Also, I have never said that you couldn't use notes or anything while you're taking quizzes or tests on here. You have 2 opportunities, as always, to do your best on this test. And remember, again, it is worth 57 points. Now, I didn't say this about the last one, but the Venn diagram, if you look down here, the due date, maybe you look up here. Yes, the due date is up here. It's due March 3rd. That's next Wednesday. It's worth 30 points and it's due next Wednesday simply because I've only gotten to see you once this week, right? So here's the Venn diagram due next Wednesday, as well as the test. If you look here, this is also due Wednesday, March 3rd, and it's due by 11:59 p.m., the same day that progress reports are due. So yeah, here we go, March 3rd, plate tectonics test. So I'm gonna stop sharing my screen at this point to see if you guys have any questions. Type them in the chat if you have any questions about due dates or about the assignments. There are 3 assignments for module 14. There's Bill Nye, there's the Venn diagram, and there's the test. If you're good to go, give me a thumbs up, a Yahoo, a yeehaw, a zippity doo-dah. Good. All right. Thank you. Okay. So this is where you're going to want to take some notes. I'm going to talk to you about earthquakes. We'll do a little refresher with Wegener, right? And then after we do that, I have a couple of videos to show you guys just to support what it is that I'm saying and maybe make it more visual for you. And then you'll have time to do some work, I think. Okay, so everybody has access to this slideshow in their Canvas, right? It's module 14.1a. And the slideshow is about geological activity. And we've been talking about the theory of continental drift, which was brought up by Alfred Wegener in 1912. And just to refresh, Alfred Wegener, German scientist, had a few pieces of evidence that he thought substantiated his claim on the theory of continental drift. However, there were many scientists that did not believe him because he was not able, Alfred Wegener was not able to tell scientists how the continents actually drifted apart. He had evidence that they were once together, but not why they split apart. And that was the hardest thing for scientists to understand and accept. They accepted, you know, his evidence, but it wasn't enough evidence for them. So back in 1912, they didn't have the technology. Late 50s, early 60s, they were able to look at the seafloor, and they noticed through magnetic striping that seafloor spreading was taking place, which means that there was a divergent boundary, which means that that helped to pull the continents apart from their once large landmass called Pangaea, like Wegener had said, but now they actually had evidence to completely support the how. So in 1960, it was accepted that the theory of plate tectonics came across, which totally replaced the theory of continental drift. And it happens at different boundaries. Now, when you have boundaries, we talked about 3 different types of plate boundaries. There's divergent, convergent, and transform. And a lot of different geological activity happens at these boundaries. And some of that activity includes earthquakes, which is what we're going to focus on for module 14. Then module 15 will focus on volcanoes. Tsunamis are largely related to earthquakes, and glaciers. Glaciers help to indicate that rock evidence that Wegener was talking about, because the glaciers carve out the rock as they move down the slope. So that's not the only geological activity, but there's plenty of others, but we're going to primarily focus on earthquakes and volcanoes. So here I've got a map. And on the map, you'll see the continents as we know them now, the 7 continents, right? But you'll also see these black lines. And along these black lines, you'll notice that there are a lot of red dots, okay? These black lines do not indicate our continents. However, they indicate the plates. Now, some continents fit on one plate, some have two plates, but you can notice at all of these plate boundaries, or at most of the plate boundaries, you'll see all this red. The red is indicative of geological activity taking place, whether it is volcanic activity or earthquake activity, activity taking place. So here we are, California, right? And the United States is on the North American plate, but it also is right next to the Pacific plate. So where these two plates meet is where there is a lot of activity that takes place. So in here, it tells you that some of that activity could be earthquakes, volcanoes, or the building of mountains. USGS is a site you might want to check out. It is United States Geological Survey. You would be able to find out a lot of great information about earthquakes and volcanoes there around the world. So here are our 3 plate boundaries. Now, divergent boundaries are boundaries in which the plates are separating or pulling apart. At a divergent boundary, what happens is that the lithosphere, which is made of the crust, and the asthenosphere, the upper part of the asthenosphere, which is the upper part of the mantle, are being pulled apart. When they're being pulled apart, there is a thinning of the crust and the mantle here. And there's what's called rifting, where it's being pushed up. So our magma is going to be pushed up, and the plates are separating. So the lithosphere is thinning out while the plates separate. We have more advanced rifting here and more thinning of the plates. And lastly, at the bottom, we have where the mantle is pushing up and is creating new oceanic crust, or a mid-ocean ridge, or at a mid-ocean ridge, right? So mid-ocean ridges and new oceanic crust, as well as volcanoes or rift valleys or rifts, are what's created at a divergent boundary. Then we have a convergent boundary. Now, the thing about convergent boundaries, and we've talked about this, and you saw hopefully in the lab that was a part of your module 13, how these different boundaries work. At a convergent boundary, a couple of different things can happen. Here I have a picture of continental crust meeting continental crust. When the two continental crusts come together, they have the same density. So when they're pushing together, they're competing, and they end up pushing up and creating what I have here is a mountain range, okay? So that rock is being pushed up and creating a mountain range. Another thing that can happen at a convergent boundary, besides continental coming together, we can have oceanic coming together. And again, those two are of the same density. So they're going to compete. They're going to compete and push up, and possibly form either volcanoes or island arcs. Lastly, at a convergent boundary, you can have an oceanic plate meeting up with a continental plate. And what happens is when the oceanic plate meets with the continental plate, the oceanic plate is more dense than that of the continental plate. So they don't really compete. What happens is the oceanic plate gets pushed underneath the continental plate, and that's what we call a subduction zone, right? So it subducts, it goes beneath the continental plate. And when that happens, it creates a trench. Now, the Marianas Trench is one of the most famous trenches in the ocean now that we have. And so at convergent boundaries, at a subduction zone, you'll have trenches. Continental, you'll have mountain ranges. If it's oceanic, volcanoes, island arcs, those all happen at convergent boundaries where the two plates are coming together. Lastly, we have transform boundaries. Now, there's a picture down here that shows a fault line, a very famous fault line in California that is associated with a transform boundary. And what happens at the transform boundary, which is in here, the transform boundary is you have two plates next to each other. And those two plates, instead of pushing against each other or pulling apart, they're actually sliding past one another. Now, if you saw the video on the lab, they use graham crackers to pretend or represent rock, right? The plates, the two plates that are coming together. And graham crackers are not smooth on the sides. They have rough edges. And so what happens is when you slide the graham crackers side by side, the little pieces of graham crumble off and break apart, right? Also, the graham cracker could get stuck on the other graham cracker, just like the rocks of the plates for the plate tectonics. And when those get stuck on each other, you can try to push, keep pushing as hard as you can. And you're building up a whole bunch of stress. Eventually, one rock is going to pass the other and is going to push past it, slide past it, releasing all of that stress, creating an earthquake. When that stress is released, that's what causes the earthquake. So earthquakes are most commonly found along transform boundaries. Here you can see a fault line, the guy that's standing next to the fault line right here. The San Andreas Fault, like I said, in Southern California is the most famous fault line that there is here. And that's at a transform boundary. Now, what I've been saying to people is, if you think about blowing up a balloon, when I was little, I used to hate blowing up balloons because I was always afraid that I was going to blow it up too much. And think of that, but once you blow it up too much, it pops in your face, right? And it scares the living daylights out of you. Think about that with your two plate boundaries. It's like when you're blowing up the balloon, you're creating so much stress within that balloon itself that if you blow it up too much, it's going to pop. Well, these plates are building up so much stress when they're trying to move past one another with this jagged rock that they build up a whole bunch of stress. And that when it eventually releases, like when the balloon pops, is going to create that earthquake. Any questions thus far? I don't see anything in my chat. So far, so good. All right. What makes up an earthquake? Here's a picture depicting that of a fault line and an earthquake, where an earthquake can take place. So where we measure the earthquake from is in the center of, or in the body of the earth, which is called the focus. This is where the earthquake originates from. And we can look at that, take measurements from that, and also right above it is what we call the epicenter. So the epicenter is found on the surface, whereas the focus is the origin of that earthquake. Depending on how deep it is going to depend on how much damage is caused. And usually what scientists will do is they will be able to figure out where the epicenter is of the earthquake, and then directly below that is the focus. When an earthquake is felt, a couple of things can happen. So this is where I really want you to take notes, okay? Because your Venn diagram asks about P waves and it asks about S waves. I'm going to talk to you about P waves. I'm going to talk to you about S waves, which are called body waves. So you might want to write that down. P waves and S waves are body waves, meaning that they are felt in the body of the earth, right? P waves and S waves are in here. The other type of wave is called a surface wave, and those would be up here on the surface. So the P wave and S wave here are body waves. Surface waves are up on the surface. Here's our P wave. So if I am a seismologist, I am a scientist that studies earthquakes. Write that down. Seismologist is a scientist that studies earthquakes. Earthquakes, when they are detected, the movement in the earth is collected on an instrument called a seismograph. The seismograph takes the measurements of the waves as they come through the earth. So the seismologist is going to look at the seismogram, which is going to be found on the seismograph. So the piece of machine that takes the measurements is a seismograph. There are different waves that can come through. Now, the first wave that comes through that's represented on the seismograph is called a P wave. A P wave, P standing for primary. Primary waves are the first waves to come through on that seismograph. Primary waves, P waves, are the waves that travel the fastest. P waves travel fastest. They're primary, they travel fastest. P waves can travel through solids, liquids, and gases. Okay, so they're primary, which means they're first. They are the fastest, and they can travel through solids, liquids, and gases. P waves also move differently than that of an S wave. P waves move longitudinally, which means back and forth, the length of it. So think about if you had a slinky, and I have a video to show you guys about this, but think if you had a slinky and you pulled the slinky apart and then it went back together and apart and together. The way that the P wave works is that it goes in one direction, which is called the velocity of propagation, and it's going to go like in and out, okay? The length of the wave, the longitudinal wave. S waves are very different. S waves, S stands for shear. Shear waves are your secondary waves. So P is primary, S is secondary. P waves come through first, S waves come through second. S waves are also slower. So you have primary is fast, S is slower. Primary waves can travel through solids, liquids, and gases. S waves can only travel through solids. Okay, so pretty much S slower, S solids, S shear or secondary. The S wave travels different than that of the P wave when the movement occurs. So imagine that same slinky, and it's moved from side to side, almost serpentine-like. That's how an S wave moves. It's called a transverse wave. So it goes in one direction, the direction of propagation, right? And it does it in a serpentine type movement. So longitudinal waves back and forth, S waves, serpentine. Okay, so you should have all the information about those two waves, which will help you fill in your Venn diagram. Lastly, we have surface waves. So here we have our longitudinal wave, which is our P wave, and it shows you the direction of the wave. We have our transverse wave, which is our S wave. And then we have our surface wave, and it's kind of difficult to see what this is doing here, but it's going in like an elliptical orbit, right? So if you had an elliptical machine, you know, it's kind of like an oval. You'll see it in the video, but it's this movement here where it goes kind of in an elliptical way. Surface waves are the slowest of the waves. So you have primary, secondary, and then surface. Surface waves are the slowest. Primary and secondary waves are called body waves because they're found in the body of the earth. Surface waves are found just where they say, on the surface of the earth. Surface waves cause the most destruction. S waves will cause buildings to drop. Surface waves, however, cause the most destruction because they're so close to the surface. If you think of surface waves, I've got a video in here where you see people surfing and they talk about surface waves as they relate to the ocean as well as not volcanoes, earthquakes. So you'll see how a surface wave actually works. Right now, that's all I have about those. Does anybody have any questions about what P waves can do, what S waves can do, what surface waves can do, what forms at different boundaries, anything like that? Let me know that you're all still alive and that you're okay. Good. Thank you, Lonnie. Thank you, Arden. Okay. Thank you, Aiden. Good. Thank you, Alex. All right. All right. Good, good, good. So I have a couple of videos to show you guys, which is going to show you how the waves actually move. And then we will chat for a second. You'll be able to fill out your Venn diagram. Here we go. I'm going to exit this. And I have a few videos. So we're going to start with this one. It's only a couple of minutes long.
There are three basic types of elastic waves which cause earthquake waves. Two of those three develop in bodies of rock. The faster wave is called the primary or P wave. It moves in the same way as a sound wave, so that as it spreads out, it pushes and pulls the rock. The slower of the two waves is called the secondary or S wave. When an S wave forms, it shears the rock sideways at right angles to the direction it is traveling in. In most earthquakes, P waves are felt first. The effect of P waves is bumping and rattling of windows. The effect of S waves is an up and down and side to side motion, which shakes the ground surface vertically and horizontally. This is the wave motion that damages structures of buildings, causing them to collapse. The third type of an elastic wave is called surface wave and can be split into two types. The first type is called a love wave. It moves the ground from side to side in a horizontal motion. This motion particularly damages the foundations of buildings. The second type is called a Rayleigh wave. Rayleigh waves move vertically and horizontally in a vertical plane, which moves in the direction the waves are traveling in. Scientists have developed a theory which states that earthquakes are caused by plate tectonics. It also says that Earth's outer shell is split into about 10 larger and 20 smaller plates. These plates move apart, collide, and slide past one another. These movements are caused by earthquake waves. An example of an earthquake caused by plate tectonics is the Peruvian earthquake in 2007. Peru lies on the boundary of two plates, the Nazca Plate and the South American Plate. The South American Plate moves 60 millimeters per year towards the Pacific Ocean and over the Nazca Plate. The tension is sometimes released through earthquakes. Earthquakes can be detrimental. In fact, in most cases they are. In Peru, there were over 2,000 casualties. Scientists have no way of foreseeing earthquakes, as it is not very easy. However, there are 3 simple steps to follow if you are in a building during an earthquake. Drop, cover, and hold on. Just remember these steps and you'll have a better chance of being safe.
Okay, so that is earthquakes and the movement of P waves, S waves, and shear waves. I'm going to show you on here really quickly just so you can see the slinky because it's very easy to visualize on here. I know they showed you with like the math cubes, but it's very easy to visualize on here how P waves and S waves move. They don't have shear waves on here. Sorry, not shear waves. They don't have surface waves. That's another clip I have, but this is just going to be first P waves and then S waves. So this indicates the P wave, how it moves longitudinally through the rock when an earthquake happens. Now here is our S wave. So you can see that serpentine movement of the slinky back and forth. And that is how the P wave and the S wave actually move. Lastly is our surface waves. I like this one because it's pretty and it reminds me of the beach. You're going to see how surface waves can affect with
Let's
an
take a look at
earthquake.
some surface waves. Welcome to Moo Moo Math and Science and Surface Waves. While the waves that travel within the depths of the ocean are longitudinal waves, the waves that travel along the surface of the oceans are referred to as surface waves. A surface wave is a wave in which the particles of the medium undergo a circular motion. Surface waves are neither longitudinal waves nor transverse waves. You know, kind of like a light. In longitudinal waves, the particles move parallel to the disturbance. And with transverse waves, the particles move perpendicular to the disturbance. In a surface wave, it is only the particles at the surface of the medium that undergo this circular motion. The motion is both at right angles and parallel when the particles move in a circle. The circular motion of the particles tends to decrease as you move further down from the surface. Large bodies of water like the ocean contain surface waves. During an earthquake, Rayleigh waves are produced and are a type of surface waves that travel near the surface of solids. The circular motion of the medium near the surface produces both longitudinal and transverse motions. Let's take a look at the anatomy of a surface wave.
Okay, so you guys don't need to watch the anatomy. It talks about the crest. It is moving like the letter is shaped. What do you mean? The S for the surface wave? It does that serpentine movement, right? Is that what you're talking about, Lonnie? Yeah. Surface waves, however, like I said, it's like that elliptical movement. It not only does it go in circular, but it kind of goes forward at the same time, like that of a ripple if you throw a rock in a lake, or like the ripple of an ocean. No, I get it. So do you guys have any questions about S waves, P waves, surface waves? Which one causes the most damage? Which one gets there first? How they travel, Alfred Wegener, the theory of continental drift versus the theory of plate tectonics, different types of boundaries, convergent, divergent, and transform. You guys, you think you're pretty well versed in that? Awesome. Okay, so science says S waves cause the most damage. Surface waves, so they said in there, P waves, because P waves and S waves are in the body of the earth, they will cause damage, yes. But depending on how deep it is going to depend on how much damage it's going to cause. Surface waves, because they're so close to the surface, they are the most destructive. When you feel, they were saying, when you feel like a P wave, and if your windows start to rattle, I don't know how many of you have been in bigger earthquakes, but I was in one in Alaska and I literally woke up because the windows were shaking and everything like that. That was P waves that came through. The S waves that come through after that could cause buildings to collapse. So it wasn't that big of an earthquake. So none of the buildings collapsed. As opposed to 1960 when they had a huge earthquake in Alaska, which took down most of Anchorage. Okay. And in 1906, there was a huge earthquake in San Francisco. You should look that up on YouTube. You can find some footage of the earthquakes. It's pretty intense, cool stuff. But the surface waves, because they're closest to the surface, they're going to cause the most amount of damage out of all of the three waves. Does that answer your question? Alaska, Lonnie said there was a big one in Alaska a couple of months ago. Alaska has earthquakes daily. They're not all very big, obviously, but it depends on where the earthquake is. as to damage caused, and Anchorage is a pretty well built area, most populous in all the state, and the state is huge. So the one in 1960 has been recorded with, one of the ones that have been recorded with the most damage. They still have a place called Earthquake Park there, where they didn't change any of the park itself, and they let it restore itself as nature would do. And you can still go and see damage from the earthquake from 1960. So yes, Alicia, now it is very cool, but living in the area is dangerous. So we live in an area in which we have the San Andreas fault line right here. And it could cause a pretty major earthquake, which is the 1906 earthquake up in San Francisco. That's how long the fault line is. It was because of the San Andreas fault line, a movement within the San Andreas fault that caused that big earthquake of 1906. Yep, it sure did. You can see, Miles said the Bay Bridge broke too. It collapsed, and you can see there's some video of like the one level of the bridge resting right on top of the other level of the bridge. So major, major damage can happen from earthquakes. Absolutely. That's pretty cool, Miles. Earthquakes are pretty interesting. I don't know if you, when you were looking into that, if you were looking into plate tectonics as well, but it's all related. So. Okay, well, you guys should be able to fill out your Venn diagram right now if you wanted to and respond to somebody else.